speaker today, Professor Clive Tadhunter, who is visiting us this week. Actually, today is his last day here. So to let you know about what Clive has done in the past, he did his PhD in Sussex, and then he did the first postdoc in St Andrews, in Scotland. Then he spent 2 years as an ESO fellow in Garching, and then he moved to the Royal Greenwich Observatory in Cambridge, not in London. And the last 20 years he has been in Sheffield. He's the head of the astronomy group there. And I had the pleasure of working with him for 2 years there. So today he's going to tell us about the triggering quasars in galaxy interaction.
So can you hear me? Yeah. So it's a great pleasure to be here. I realise it's, I think it's 10, 15 years since I was last in the IAC. Too long, I think. And since then, GTC's been built, and I saw it last week. Absolutely amazing to see it. And today I'm going to talk about quasars, triggering quasars. And it's appropriate this year to be talking about it because it's exactly 50 years since the discovery, the first steps were taken to discover this object, 3C273. And of course, the big thing about quasars is that they're incredibly luminous objects. They're the most luminous objects that sustain their activity on long time scales in the universe. And they're very important in that respect. But if you were to have looked at quasars 30 years ago, the perspective was very much that they're exotic objects. They're extreme physics, perhaps interesting. And the other thing about them was they were bright, so they stood out, and you could detect them at very high redshifts, and you could use them to perhaps probe structures a long way away in the universe. But it was thought that they weren't really necessarily important for the formation of galaxies, say 30 years ago. But over the last 20 years, our perspective of quasars has changed. And it's now thought they may be central for galaxy formation and play a very important role in galaxy formation. And really, there are two indirect pieces of evidence for this. The first is that if you look at the evolution in quasar activity as a function of redshift, cosmic epoch, which is given by this curve here, you see this curve that shows the evolution in radio-loud quasar activity, then it's very similar to the star formation history of the universe. So if you look at the star formation history, these points here, this is the famous Maddow plot, which shows the star formation density as a function of redshift. Of course, there's a lot of uncertainty at the high redshift end because of reddening corrections and that sort of thing. But there's a similarity between the evolution of activity with redshift and the evolution of star formation. And both things are thought to peak at about the same epoch of about redshift 2. So that suggests that the evolution of activity and galaxies in general is linked. But then a bit later, people discovered with Hubble Space Telescope observations that the black holes in the center of the galaxies, their properties are very strongly correlated too with the host galaxies. So there's this famous correlation between the mass of the black hole and the mass, the velocity dispersion, and the mass of the host galaxy that's the quasars in. So there's a very strong correlation. And again, that suggests that the evolution and formation of the black holes is very closely tied in with the evolution and formation of the galaxies, particularly the bulges of the galaxies. And these two things actually form together. So how do we explain these trends? Well, the left-hand plot, the star formation history and the evolution of quasar activity, you can perhaps explain that in terms of triggering. Because when galaxies accrete gas, by mergers or cooling flows, whatever it is, the gas will become concentrated into the central regions. You have a large density of gas. That will give you star formation, but it will also fuel the black hole and give you quasar activity. So perhaps we can understand the trend in evolution with redshift in terms of triggering and accretion of gas. Whereas on the other hand, the correlation between black hole mass and host galaxy properties has been explained in terms of feedback. And the idea is that as you accrete gas, you form stars in the bulge of the galaxy. You also fuel the black hole. The black hole grows in mass. The activity gets stronger and stronger, and eventually the quasar blows out all the material in a wind, and that stops any further star formation and black hole growth. So it's a kind of self-regulation that the black hole and the outflows and feedback associated with the black hole actually regulate the growth of the bulge of the galaxy. So that's the idea. And the other thing that is potentially important for is explaining the luminosity function of galaxies. So the points here show the distribution of the number density of objects at different luminosities. This is what people working in galaxy evolution always try to explain. And the lines here show different attempts to explain the evolution. And the point is that if you try to explain the luminosity function in semi-analytic models without having AGN feedback, you get the dashed line there. And the problem is that the gas in the dark matter halo cools very effectively, and you form too many high mass luminous galaxies at the high luminosity end of the luminosity function. But if you switch on the feedback, you get this lower curve, which matches very well the galaxy luminosity function. And the idea is that the AGN heats up the gas and stops it from cooling, so you don't form so many high mass galaxies. So the feedback from AGN may be important also in explaining fundamental properties of the galaxy population, like the luminosity function. That's the idea. But of course, if we want to understand this feedback effect and incorporate quasars into our galaxy evolution models, we really need to understand how they're triggered. And that's what I want to concentrate on today. So, as we know, the luminosity from quasars is derived from the accretion of material close to a supermassive black hole. And there's a conversion of gravitational energy into heat and light, and that happens very efficiently. But in order to see the quasar activity, we have to get the gas very close in to the centers, within a fraction of a parsec into the accretion region, the accretion disk around the black hole. And the big problem is how you get the gas from kiloparsec scales down to sub-parsec scales, a tiny fraction of a parsec. And in order to do that, the gas needs to lose a lot of angular momentum. And so in terms of triggering, that's the problem we face. We've got to get the gas in there. And because quasars are thought to last for millions of years, we've got to get the gas in there on that sort of time scale. We've got to have sustained infall in order to see the quasar on the right sort of time scale. So if we look at the different triggering mechanisms for doing this, then one way to do this is mergers. So if you merge two galaxies together, the tidal torques associated with the mergers drive gas towards the center, and you can get large concentrations of gas in the center, and that could potentially fuel the quasar for the right sort of time scale. But it's not the only mechanism. So the other possibility that has been looked at quite a lot is secular processes like galaxy bars, which are just there in the galaxy anyway, and they can also drive gas to the center and fuel the quasar activity. Then if we look at giant ellipticals in clusters, another possibility is accretion of gas from the hot gas halos. So one way this can happen is that the hot gas can be directly accreted by the black hole. So you've got lots of hot gas, it's got a high density, and it can be accreted in a spherical, perhaps Bondi accretion, and that can fuel the activity. Because the gas density is low, this won't give you a very luminous quasar, but it can explain low luminosity AGN activity. And then the other possibility is that the gas cools from the hot X-ray halo, and then the cooling clouds drop into the center in a cooling flow, and that can also fuel the quasar activity. And then the final possibility is that you can have cold flows along the large-scale structure, filamentary structure in the universe, and those large-scale flows can also fuel and trigger quasar activity. And then the other point to make is that there may be evidence of a dichotomy in triggering mechanisms, that it's possible that high luminosity AGN quasars can have a different triggering mechanism to low luminosity quasars. And there is some indirect evidence for this. So if you look at this top right-hand plot, this is the black hole mass velocity dispersion correlation. And the points highlighted here in red and black are classical bulges. And for classical bulges and spheroids, you get a good correlation between the velocity dispersion and the mass of the black hole. Okay. But if you look at objects with pseudo bulges, so these are bulges that have more angular momentum, they're a bit flatter, they're not like classical bulges like you see in M31, for example, in the bottom plot, then the pseudo bulges, they don't show a correlation between black hole mass and velocity dispersion. Admittedly, it's quite a small range of velocity dispersion that's covered, but there's not such evidence for a good correlation. And one interpretation of this is that these represent different formation scenarios and different modes of activity. So it's thought that bulges and spheroids that you see in the top plot are formed by mergers. So you need a merger to form a bulge or a spheroid. And when you do that, you get a lot of gas infall and you get a quasar. So at the top here, the plot at the top may be associated with quasars as bulges forming mergers. Whereas in the bottom plot, pseudo bulges, in that case, you may have a more secular process, bars and that sort of thing that fuel the activity. And that may be associated with low levels of activity, as sort of Seyfert-like moderate activity that we see in the nuclei of a lot of galaxies. So these two plots may represent different formation scenarios and could reflect the fact there's a dichotomy between high luminosity AGN associated with bulge formation and lower luminosity AGN associated with Seyfert-like activity. And in fact, if we look at the lower luminosity AGN, so these are typical Seyferts like NGC 4151 or NGC 1068, that sort of thing, then there's very little evidence for mergers, the sort of mergers that would give you quasar-like activity. So there have been a few studies over the last few years that have looked at the host galaxies of moderate luminosity AGN selected at X-ray wavelengths and compared them with control samples, very large control samples in deep fields that are matched in absolute magnitude. And what you see is that on the left four panels there, you have the AGN host galaxies, and on the right, you have some inactive galaxies. And they looked at hundreds of AGN and thousands of control sample galaxies. And the conclusion is that they don't find any differences between the active and inactive galaxies in terms of their morphologies. So they don't find evidence for strong mergers in most of the AGN, and a similar thing for the control sample of inactive galaxies. So this supports the idea that moderate luminosity AGN are triggered and fueled by secular processes inside the galaxies. There's nothing special going on. There's no sort of event that's actually a big event that's causing the activity. So that kind of fits in with the idea that moderate luminosity AGN are fueled secularly. So what about quasars? So I'm going to concentrate on quasars in this talk. Well, the requirements in terms of accretion of quasars are much larger than they are for moderate luminosity AGN like Seyferts. So I should define first of all what I mean by a quasar, and I'm going to define a quasar to be an object that has a bolometric luminosity of about 10 to the 38 watts or above. That corresponds to a B-band absolute magnitude of less than minus 23 and an O3 luminosity of 10 to the 35 watts. So that's what I'm defining to be a quasar. And to get that level of activity by accretion, the black hole needs to accrete more than about 0.2 solar masses per year to get that sort of level of activity. Quasars can actually be 100 times brighter than this. So this is the lower end of the quasar range, but this is what I'm going to define a quasar to be. So that may sound relatively modest, only 0.2 solar masses a year to give you a quasar. But the point is that you sustain that activity on a timescale of somewhere between 10 and 100 million years. Okay? So the amount of material that you've got to accrete over the whole lifetime of the quasar is millions of solar masses. So you've actually got to feed between 1 million and 10 million solar masses into the black hole. And the total reservoir of gas that you need in the bulge, because you're forming stars as well, is much larger than that. So there's a requirement to accrete a lot of gas to have a quasar. And one of the most popular ways of doing this is by a merger, because a merger is a particular event which is capable of feeding a large amount of gas into the nuclear regions of galaxies on the right timescale. And we now have beautiful simulations that show this. So this is a lovely simulation by Di Matteo that came out about 7 years ago. And it shows the merger of two spiral galaxies of equal mass. And so they collide there. You might have a bit of a star formation associated with the shocks. So that's the first pass. And then the two galaxies pull away again. The gravitational potential becomes very elongated. And what you see is that the gas then flows towards the nuclei of the two galaxies. And gas gets concentrated in the nuclei. You get lots of star formation there. But you also feed the black holes. And those black holes and the quasars drive outflows. You can see the outflows happening. That drives the gas out. And eventually the two black holes in the galaxies merge together. And you get even more feedback because of the energy associated with that. You get an explosion. There you go. So it's a kind of seductive picture of what might be happening in these systems. And I think the question is it just a cartoon or is it reality? Because what these models do is that they predict the star formation as a function of time in the merger. So I think it's important to make the point that a merger isn't a thing that happens instantaneously. The full merger from start to finish can last a gigayear, and the tidal features associated with that can last for a gigayear. And most of the action actually happens in the stage where the black holes merge together. So at this stage here, you get a peak in star formation. So this is the star formation rate as a function of time, associated with when the black holes merge together. This is for galaxies that have big bulges. But at the same time, you get a peak in black hole accretion rate. So the bottom plot shows the black hole accretion rate as a function of time. And you get a peak in the black hole accretion rate at about the same time, perhaps slightly delayed compared with the starburst. So what you expect is that there's going to be a massive starburst, but also you get this peak of black hole accretion. And the thing is, you can ask, well, when is this object appearing as a quasar? Well, as I say, to have a quasar, you need to have a mass accretion rate, and this shows the mass accretion rate here, of greater than 0.2 solar masses a year. So it's only in this narrow window around the peak that, in this model, the object would appear as a quasar. So in many of these models, the quasar only appears for a very short time around the peak of coalescence of the black holes. So that's the idea. But I think you have to be quite skeptical when looking at these models. And that's because they make lots of assumptions. There are lots of free parameters in the models. And they're trying to fit the observations post hoc. So we always have to be a bit cautious about that. And I think one of the main problems with these models is, particularly this one, is that its resolution is very poor. So there's the cell size in the simulation is about 100 parsecs. And basically anything that gets within 100 parsecs of the central black hole is immediately accreted and gives you quasar activity and fuels these outflows. But of course, it's actually a big problem in reality to get the gas from 100 parsec scale actually onto the black hole. And that's not simulated in this at all. So these models are, they're useful tools for trying to understand what's going on. But I think we have to be a bit careful about believing them in detail, because a lot of the important physics of accretion in the central regions isn't covered. So how do we test these models? Well, an obvious approach is to just look at the morphologies of active galaxies, quasars, radio galaxies, and that sort of thing, to see if they look like mergers. Do these objects look like mergers? And does that provide evidence for triggering? So we've undertaken a large survey, and this is the work that Christina's been doing over the last couple of years. And we looked at a very large sample of radio galaxies, 46 southern radio galaxies at intermediate redshifts. And most of them are what we call narrow-line radio galaxies. They've got strong emission lines. We have some quasars there as well, and also some weak-line radio galaxies. But most of these objects have luminosity that tells you that there's a hidden quasar or a direct quasar in the center of the galaxies. So these are quite luminous active galaxies that we're looking at. And the important thing is that they're radio galaxies, radio-loud active galaxies that we're looking at. And the advantage of radio-loud active galaxies is that they're invariably associated with early type ellipticals. And that means it's much cleaner to look for signs of mergers, tidal tails, starbursts, that sort of thing, because they're quite smooth before the merger. So it's actually it's easier in these sources to look for signs of mergers and triggering of the activity. So we've imaged all these sources very deeply with Gemini, and this shows some of the results that Christina's obtained. This is a selection of the images of the radio galaxies that we've looked at. And the bottom line is that we find evidence for tidal features in a very large proportion of the sample, 85%. But the interesting thing is that we find a very wide range of diversity in features. So if you look on the left there, you see objects where there are two nuclei. And in the top case, you can see that the galaxy is actually linked to another galaxy at the bottom by a bridge. The one below that, you can see two nuclei quite close together, about 30 kiloparsecs apart, very distorted. So we're seeing those before the peak of the merger. We're seeing those before the coalescence of the black holes. Whereas in the center two panels, you see very highly disturbed galaxies. And that's what you'd expect for an ultraluminous infrared galaxy, a merging system. But on the right, you have systems where the signs of mergers are quite subtle, that you can just see, I think you can just see their faint shells, which are consistent with what you see in nearby ellipticals. So we see a wide diversity of properties. So just to summarize that, overall, we see 85% of these features. But the interesting thing is that in about a third of cases, we're seeing the objects before the nuclei have coalesced. So we're seeing them in, before what we call the peak of the merger. 56% show tidal tails. They're single nucleus systems, shells, and dust lanes, but a very wide diversity of features. And 15% show no signs of any disturbance. So this supports the idea that mergers trigger the activity because we see these features. But there's a wide diversity there. I think it's important to stress that. And although we think the objects are triggered by mergers, these results suggest that they could be triggered at different times in the course of a merger and by different types of mergers. So it's not just one thing going on. And the other thing is that we see evidence for dichotomy. Remember earlier I said that the high and low luminosity sources may be triggered in different ways. Well, we see this in radio galaxies directly. Because if you look at the quasar-like ones, these are the ones that have got very strong emission lines. We call them strong line sources in our sample. 94%, essentially all of these sources show tidal features at quite high surface brightness. Whereas we look at the weak line ones, which have radio jets, but they don't have much nuclear emission line activity, only about 25% of those show tidal features. So this suggests that while the more luminous ones can be triggered in mergers, the less luminous ones may be triggered in a different way, perhaps by accretion of the hot gas rather than a merger. So you've got this dichotomy. So that was radio-loud active galaxies, but they're, of course, only a subset of the total AGN population. So the other thing we've done is we've looked at a sample of radio-quiet objects. These are quasar-2, so they're luminous quasar-like objects in which the quasar is actually hidden from our direct view. And this is work done by Patricia Bessiere, who gave a talk here a few months ago. And basically, we get the same result. So here's a selection of the images that we obtained. We looked at 20 objects. And again, we see evidence for a lot of tidal features there at high surface brightness. But also, we see a wide diversity. So a large proportion of objects, about 70-80% show tidal features. But again, we see double nuclei. We see a wide diversity of features, which suggests that the AGN may be triggered at different stages of the merger. But just detecting the tidal features is not sufficient, really, to show that the objects are triggered by mergers, because we know that even if we look at quiescent nearby galaxies, that a lot of them also show tidal features. So, for example, 20 years ago, Main and Carter did a survey of nearby ellipticals. It was a photographic survey, so not particularly sensitive. And they showed that 10% of nearby ellipticals show tidal features in the sense of shells. So they show sharp shell-like features, which are thought to be due to minor mergers, the elliptical galaxies accreting smaller galaxies. And this is just with photographic plates. And they were only looking for really sharp shell features. So if you take less regular tidal features and, modern detector technology, then it could be that a large proportion of nearby quiescent ellipticals also show tidal features. And if that's the case, then perhaps it argues against our idea that our radio galaxies and quasars are triggered in mergers. So what we need to do is look at control samples of elliptical galaxies to compare with our radio galaxies. And this is work that Christine has done. And basically what we've done is we compared our radio galaxies with two control samples of quiescent ellipticals. The first we looked at is called the Obey sample. And this is a sample of very nearby galaxies that have been observed, very deeply with CCD technology. And what we find in that sample is that 34% of them show tidal features at a high surface brightness level. So by high surface brightness, I mean surface brightness brighter than about 25.5. So that's the sort of limit of the Malin and Carter photographic survey. So nearby elliptical galaxies show 34%, but in the radio galaxies we find a higher proportion, 79%. And one of the measures we have of the strength of the merger is the surface brightness of the tidal features, because the stronger the merger, the more major it is, the more gas-rich it is, then the higher the surface brightness of the features we expect to see. So as well as just looking at the proportion, we find a higher proportion in the radio galaxies than in the nearby elliptical galaxies. We've looked in detail at the distribution of surface brightnesses. And what we find is that the surface brightnesses of, see if it works better this way. There we go. The surface brightnesses distribution of these quiescent galaxies is, it's quite a bit, I think I've changed the slide, haven't I? Yeah, it's quite a bit fainter than in radio galaxies. So it's not just that a lower proportion of the quiescent galaxies show tidal features. It's also that the tidal features that we do detect in those tend to be lower surface brightness, suggesting that it's weaker mergers. Whereas in the radio galaxies, you get a higher proportion and you find a higher surface brightness. So that's low redshift objects. We've also done this for higher redshift objects in the sample, using a sample of elliptical galaxies from the extended Gross strip. In this case, the distinction is a bit less clear-cut. We find that 50% of the ellipticals in the Gross strip have high surface brightness tidal features, compared with 95% of the radio galaxies. There's still a difference there. But again, we find that the quiescent galaxies have lower surface brightness on average by about magnitude. So we find a higher proportion in the radio galaxies with these tidal features, and their surface brightnesses are higher, which supports the idea that triggering is by mergers. But what you notice here is that actually there's a large overlap in the features. This doesn't work a lot of the time. Oh, there it is. Yeah. So there's actually a large overlap. So quite a lot of the elliptical galaxies have similar surface brightness tidal features to the radio galaxies. And if you take into account that, of course, elliptical galaxies in general are much more common than radio galaxies, then the surface density of these objects, the quiescent tidally disturbed galaxies, is actually much larger than it is of radio galaxies. So is that a problem for the merger hypothesis? Well, I think it's important to realize that the timescale of the quasar activity is much less than the timescale of the merger. So it's possible that in a merger, the tidal features can be visible for timescales of a gigayear or so. So we'd be able to detect them over that timescale, starting just before coalescence that's represented by this line here, but all the way up to about a gigayear, we can see the tidal features. On the other hand, the quasar activity, we think, only lasts for between 10 million and 100 million years. So it's a much shorter phase. So the ratio of the times at which the quasar is active to the time to which the features are visible can be quite small. So you'd only expect, if you looked at tidally disturbed elliptical galaxies, a small percentage, perhaps between 1 and 10% of them, to show quasar activity at any one time. And in fact, we can turn this argument round and we can ask the question, do all these morphologically disturbed elliptical galaxies go through an active phase, an active quasar phase. So what we can do is that we can estimate what we'd expect the ratio of the densities of quasars to disturbed ellipticals to be. And that's just the ratio of the timescales, and that comes out as between about 1% and about 10%. And then what we can do is we can compare that expectation with the observation. So we can compare the actual number densities of quasars to the number densities of disturbed elliptical galaxies with the same absolute brightness. And the answer we get for that is about 10 to the minus 3. So what that's telling us is that that ratio is about 10 times less than we'd expect if all disturbed elliptical galaxies went through an active phase. So this is telling us that actually there's something else going on, that just having tidal features and having some sort of interaction isn't enough to trigger a quasar. So there's probably something else going on. It could be how major the merger is, whether it's a major merger, whether it's gas-rich, gas-poor, but it's not just any old tidal interaction that's going to give you a quasar. So what else is going on? So obviously we need more information about the mergers. And the trouble is that just with the morphologies alone, we can't deduce too much. So we need more information. And the other information that we can have is the star formation history. Because the other thing that happens in the merger is that you get a peak of star formation about here that coincides with the coalescence of the black hole. So if we can actually detect that star formation, we can use that to learn more about the merger where it's a major merger, and also the timing of the activity relative to the peak of the merger. So it's important to look at the star formation properties of these systems. And the first place we looked to do this is in the optical UV, to look for the optical UV signs of star formation activity. And actually, this is quite difficult to do in radio galaxies. The initial photometric measurements of radio galaxies showed that they did indeed have a UV excess. So if you plot their V minus R color against redshift, the radio galaxy points are down here, whereas this red curve is what you get for the passive evolution of elliptical galaxies. You get this red curve here. So the radio galaxies are much bluer than you'd expect for passive evolution. And so this may be telling you that there's lots of star formation going on. And in fact, that was the initial interpretation, that this difference here was due to star formation in the host galaxies. The trouble is that these systems are extremely active. There's a lot of things going on in these active galaxies. So you might have star formation associated with the accretion and the disks, but you also have jets. The jets can shock the clouds. The shock clouds can emit nebular continuum that radiates in the UV. You can have scattered light in the ionization cones of the AGN. That scattered light will give you UV radiation. The AGN will photoionize the gas. The photoionized gas will emit a UV continuum. You can also have some direct AGN light leaking through the edge of the dust structures. So there are lots of components there, and a lot of these components can contribute to the UV. So when we see a UV excess in radio galaxies, it's not necessarily due to star formation. And so you need very good data to separate the real star formation from the AGN contribution. So you need polarimetry, for instance, to see the scattered AGN light. You need emission line spectroscopy to distinguish the nebular component. And in fact, when you do that, you find that less than 35% of nearby powerful radio galaxies show evidence for star formation at optical wavelengths. So if they're all triggered at the peaks of galaxy mergers, you'd expect many more than that. And what we've done is we've gone away and we've looked in more detail at the ones that do show star formation. And so this is one of the ones we looked at in detail. This is 3C305. And you see it's got strong tidal tails, which suggests it's been in a merger. And if you look at the spectrum of this object, then the spectrum is actually quite red. If you took the colors of this object, it would appear quite a red object. But in fact, it shows strong Baumann lines in absorption. And if you model this, you find that you need a reddened young stellar population, an old stellar population to model the spectrum effectively with a spectral synthesis model. And the interesting thing is that the age of the stellar population is about 0.5 gigayears. And what that suggests is that the radio source that we're seeing now has been triggered, almost half a gig-a-year after the peak of the star formation activity. And the mass is also very large. The mass in the young stellar population is about 10 to the 10 solar masses. So it really suggests this is a major merger, and you formed a lot of stars. But we're seeing the AGN activity a long time afterwards. So there's a delay in this case between the triggering of the starburst and the triggering of the AGN, which goes against, again, the merger models for the quasar activity. But that's one case. But this is another case, and it's completely different. This is 3C459, and it's much bluer. It's got stronger Balmer lines, a much larger contribution from a young stellar population. And it's very luminous. And in fact, it's an ultra-luminous infrared galaxy, but it's also a radio galaxy. And in this case, the stellar population is much younger. It's about 50 megayears. And again, the mass of the stellar population is quite large. It's about 4 times 10 to the 9. So it's a major merger, and you've got lots of star formation. But in this case, the age of the stellar populations is similar to the age of the radio source and the activity. So the AGN's been triggered at the same time as the starburst at the peak of the merger. So we have two things going on. The first thing to say is that only a minority of powerful radio galaxies show any evidence for star formation. But if we look at the ones that do, then some have very young age stellar populations, less than about 0.1 gigayears, 100 megayears, and they're highly morphologically disturbed. They look like ULERGs, and we believe that the AGN has been triggered at the peak of the merger, which is what the models suggest. But then we have a whole bunch of objects where we see much older young stellar populations, and it looks like the AGN has been triggered sometime after. They tend to be less luminous. So whereas in the first case they look like quasars, in the second case they're less luminous AGN. And I think the overall conclusion of this is the same as the morphological study, that we see a wide diversity of things going on. Some objects are triggered at the peaks of mergers, but some are not. Some are triggered at different stages. But you might argue that actually looking at optical UV wavelengths is not a good way of looking for star formation, because we know that major starbursts are dusty and a lot of the star formation may be hidden. So an alternative approach is to look at far infrared wavelengths. So over the last few years, we've gone back and looked at our sample again in the far infrared using Spitzer and more recently Herschel to try and look at the star formation activity, because a lot of it may be hidden. And the reason for doing this, of course, is that if you look at major mergers like ULERGs, which invariably disturb merger systems, then we know that the starbursts there are very dusty. And so a lot of the luminosity associated with the starburst is absorbed by the dust and gets re-radiated at far infrared wavelengths. So it's possible that a lot of the star formation in radio galaxies is actually hidden by dust, and we're not seeing it at optical wavelengths. So what we've done is that we've observed our samples. So we've got the 2 Jansky sample I talked about earlier, but also a 3C sample, and we've observed them with deep observations with Spitzer, and we get very high detection rates. So we've got a good completeness for this survey. And the good thing is that we have all our optical information. So we have the information on the optical starburst properties and all the AGN luminosity indicators as well. And what we've done is that we've taken the photometry with MIPS, and we've worked out the 24 micron luminosity. So 24 micron is the mid-infrared. And we compared it with the O3 luminosity, which is a proxy for AGN activity. So we believe that the O3 luminosity is a good indicator of AGN activity in these sources. And what we find is that we get good correlations. So at the top plot, you've got 24 microns, that's mid-infrared. We believe a lot of that radiation comes from the torus, and it shows a good correlation with the O3 luminosity. So we think that the dust in the torus is largely heated by AGN illumination. But the interesting thing is that we go to far infrared wavelengths, this is now 70 microns, we also get a correlation with the same slope, which suggests that rather than being heated by star formation, in a lot of objects, the far infrared is also produced by AGN illumination of the dust, not necessarily in the torus, but on a larger scale in the narrow line region. But what you notice is that the scatter in this lower plot, the far infrared plot, is larger than at mid-infrared wavelengths. So how do we explain that? Well, this turns out to be related to the star formation, because what we can do, this is the plot again, and what I've done is that I've highlighted the objects that show optical evidence for star formation activity. You know, remember about 30%, 35% of the sources in our sample show optical evidence for star formation activity. If we highlight them here with stars, we find that they all lie above the correlation. So we think that actually, just as at UV wavelengths, in the far infrared, you have to be careful in trying to distinguish between star formation and AGN activity. And we think what's going on is that, the underlying trend is AGN heating, that the more luminous the AGN is, as indicated by the O3, then the more illumination of the extended dust in the narrowline region and the torus is, and the more far infrared radiation you get by AGN heating. But in a subset of cases, you get starburst heating, which boosts the far infrared radiation in about 30% of cases. So there are two things going on. And again, we have to be careful to distinguish between starburst and AGN heating of the dust. It's generally assumed, actually, in most studies of active galaxies in the far infrared, that all the far infrared is starburst heated. But we think that a lot of it actually may be AGN heated. So if we summarize, we put it all together, the information about star formation in radio galaxies, then if we look at optical wavelengths, we've done 3 surveys, and they all show the same thing, that about somewhere between 25% and 30% of the objects show evidence for star formation at optical wavelengths. And now we've done the far infrared survey to look for star formation that may be hidden in the same objects, and we get the same result, that about a third of them show evidence for star formation. We've also done mid-infrared spectroscopy to look for the PAH features. That gives the same result as well. And so we get the same result at optical and far infrared. There's no evidence for a major hidden star formation that we're not picking up in the optical. And about a third of radio galaxies show evidence for strong star formation activity, however we do it. And this is important because the lack of star formation activity that we see in about 65% or more of objects tells us that the activity can't be triggered in major gas-rich mergers in all radio galaxies. Okay, it's triggered in major gas-rich mergers in some of them, but if it was triggered in major gas-rich mergers in all of them, or close to the peak of those mergers, then we'd see the star formation activity, and we don't see it at any wavelength we look at. So that's important. In terms of what we do next, I've talked a lot about the stars in these systems, in terms of the morphologies and in terms of the star formation histories. But what I haven't talked about is the gas. And I think the key observation in the future to take this work forward is to look at the cool gas and try and understand what's going on with that. And I think one really important thing to do is to look at the gas reservoir, because we need a lot of gas. If we're going to trigger a quasar and sustain it for millions of years, we need to accrete a lot of gas. So what is the gas reservoir in these systems? Well, a quasar must accrete more than about 0.1, 0.2 solar masses per year to maintain the activity, to see the level of activity. That seems relatively modest, but as I said, quasars last for between 10 and 100 million years, and that means that just accreting onto the black hole, we've got to accrete between 10 to the 6 and 10 to the 7 solar masses. But that's not it, because we know from the black hole mass host galaxy correlation that for every solar mass accreted by the black hole, we've got to form 1,000 solar masses of stars in the bulge to maintain the black hole correlations. So that means that the total requirement in the merger for gas accretion is between 10 to the 9 to 10 to the 10 solar masses. So we've got to accrete a large amount of gas. The accretion process is inefficient. Only 1,000th of the gas finds its way into the black hole. So in order to sustain this activity, we've got to accrete a large amount of gas. So one of the things we want to test here is whether, if we look at our population of quasars, radio galaxies, whether they really contain this amount of gas. And I think an excellent instrument to do this, of course, is Herschel. Because what we can do with Herschel is that we can search for the cool dust emission. So this shows an SED of a radio galaxy, some recent Herschel results we've obtained. And the bump you see on the right there is the cool dust peak in this source. And so by fitting the SED of that peak, we can work out the dust mass. We can use the standard dust to gas ratio and work out, whether there's really a sufficient reservoir there for the quasar, the sort of reservoir we'd expect. And we're lucky because we've got our 2 Jansky sample approved as a must-do program. So we're doing all our objects and measuring their dust and gas masses using Herschel. So that's a good thing to do. But just measuring the reservoir is not enough. And the reason for that is that we know that if we look at a number of nearby elliptical galaxies, then they have lots of gas in them. They actually have lots of cool gas in them. It's not that common, but a significant fraction of nearby ellipticals actually have quite a lot of gas and dust in them. And this is a case in point. This is called Cygnus A. It's the nearest giant elliptical galaxy, and it's got this kiloparsec dust lane crossing it. It's got very clear dust lane. And the mass of gas measured in CO, and you can also do it by the dust in this source, is about 3 times 10 to the 9 solar masses. So the mass of gas and dust is about the same as the Milky Way, okay, in this system. But the thing is, although it does have radio jets, it's not a quasar. It is sort of active. It's the nearest radio galaxy, but its level of activity is orders of magnitude, factors of 100 less than in a typical quasar. So it's quite a quiescent system. I mean, it looks bright because it's nearby. It does have radio jets, but it's not a quasar. So you have to ask the question, why isn't Centaurus A quasar? It's got just what we need. It's got this large gas reservoir. Why isn't it active? And why aren't other elliptical galaxies that have large reservoirs of cool gas, why aren't they active too? Well, the probable reason for this is the dynamical state of the gas, because you can do very detailed studies of the gas kinematics in the center of Centaurus A using H1, CO at very high resolution. And what they show is that the gas in this case is actually very quiescent. It's in equilibrium. It's just rotating around in the center. It's a warp disk, but once you take into account that warp, then it's kinematically quiescent. There's not much evidence for inflow or outflow. It's all settled down. And so in order to produce the weak radio jets that we see in this case, you don't actually need much gas accretion. And we don't see much evidence for much inflow in this source. So I think the other element that we need is to look at the kinematics in these cases. Because just having a reservoir is not by itself enough to give you a quasar. You need to get gas into the central parsecs of the galaxy to trigger the quasar activity. And the thing is that if that gas is settled down and it's in equilibrium, then you're not actually going to see the quasar activity. And that's what's happening in Cen A. Cen A might have been a quasar when the merger that gave the dust lane originally occurred. But since then, the gas has settled down and you don't see the quasar activity now. So I think the other really important thing and the other really exciting thing is ALMA, because ALMA will be capable of mapping the kinematics of the gas in nearby quasars, nearby radio galaxies, on a scale of less than 100 parsecs. And we'll be able to do 2 things with ALMA. One is we'll be able to look at the CO, so we'll look at molecular lines, and we'll be able to check the reservoir. So we'll be able to do the same thing as we do with Herschel, and check that we haven't missed anything with Herschel and look at the gas reservoir. But more importantly, we'll be able to look at the kinematic state of the gas. So what we'll be able to do is have a look on a small scale in quasars and see how the gas is moving compared with objects like Cen A, where it's in equilibrium and it's settled. I'm not quite sure what we're going to see. I mean, maybe we'll see some inflow. That's what you might expect, some sustained inflow of gas. But it might just be that these systems are highly disordered in the center. I'd expect them to be highly disordered because that's part of the dissipation process of the gas. So I think there are very exciting prospects to make real progress in this field with ALMA. So just to conclude my talk, I think there really is clear evidence that luminous quasar like AGN are triggered in galaxy interactions. But it's not simple. It's not as simple as suggested by the merger models. we don't just see these objects triggered at the peaks of major mergers, but we see a variety of different morphologies which suggests that quasars can be triggered at different times in different types of mergers. And I think to make real progress with this, we need to look at the gas, how much of it there is in these galaxies and how it's moving. And I think that's the way forward in the future. Okay, thank you.
Thank you, Clive. We have time for some questions.
Is it okay? You mentioned at the beginning that the numerical simulations of galaxy mergers don't have the resolution to go to the disk that
the one I showed doesn't.
Yeah. But in any case, you have repeated several times that it's hard to go from the kiloparsec scale to actually to the parsec scale of the disks. So what are the ideas that people have in mind to really go from this kiloparsec to the details?
Yeah, well, I think people have started to do this actually, because what you can do is you can take the input from the large-scale simulations and then have a smaller grid in the center. And theorists like Philip Hopkins are doing this, and they're doing much higher resolution simulations of the center. So you can do that, but there's so much to take into account. I think the problem is that it's not just a question of the gas flowing. The thing is you get star formation there, and the star formation can either accelerate or can impede the activity. Because what you can do is you can get a starburst in the very center on the scale of the torus. And if that starburst is too strong, the feedback effect associated with the supernovae can actually blow the gas out and make the activity less. But if the starburst is not too strong, the stellar winds associated with the starburst can feed the quasar. So I think people have started to do subgrid models, but it's incredibly complex. There's so many things to take into account. So I think there could be progress there, but I always have a bit of uncertainty about whether they've taken all the processes into account in the right way at the right level of detail. So I think the way ahead is doing things on a smaller scale. People are doing that, but you've got to put lots of physics in, and there's even more free parameters to take into account to do it in detail. So I think we need good observations to constrain. I think we need good observations to constrain what the theorists are doing. Yeah.
Okay, thank you.
I don't know if I understood right what you said, but one of the slides we're discussing how much gas do we need to feed this these quasars, and you made the argument that you need something like around 10 million solar masses to feed the AGN over its lifespan, something like that.
Yeah,
do you understand more or less? And said, but on top of that, you also need a lot of gas to create the stars enough to keep this correlation between the mass of the black hole and massive bulge. But I don't know if that argument is it's really necessary. In the sense, that second part, in the sense that, one thing is having the mass of the black hole, and the other thing is having the gas to create the AGN activity, because, you may have the black hole created at the same time of the bulk of the stars with these bulges a long time ago, and then in merger episodes, you feed the gas to do the fireworks, so to say.
Yeah, well, you're right. Especially if you take a large bulge, an elliptical galaxy, and sort of extreme, a lot of that, the stars there may have formed a long time in the past. So I think it's a question of what proportion of stars you form in the merger. Because you may be right, if it's a small proportion of stars, it may not have that much impact on the whole thing. But if you're forming a large proportion of the stars, then the two things have got to be tied together. And it's also, of course, it's worth bearing in mind that people talk about this correlation, but there is a lot of scatter there as well. So there's a bit of leeway. I think the other argument to make about that, though, is that aside from the black hole mass correlation, the process of accretion onto black hole is probably going to be inefficient. Okay. So it's likely you're going to have to get far more gas into the center anyway, whether you're forming stars in the bulge to feed that small proportion of gas into the black hole. Because, of course, there'll be feedback effects that try and stop it from going in. You're bound to form some stars. So I think aside from the black hole mass correlation argument, you're going to need a lot more gas.
That I agree, of course.
Yeah, okay.
Yeah, first two caveats on, and then a question.
Yeah.
Regarding the age regime that you likely to be in the range of 0.5 to 1.5, something like that, gig a year that you have shown. The first caveat is that this range is also the contribution of the AGB phase, which is uncertain. The modeling is quite large. So as far as you move to the blue, the better for getting a more accurate age. On the other hand, if you are working in the blue with for example, with the Balmer lines, might be filled in by emission. So just these two caveats, okay? Regarding the question is on the light of the relatively recent findings that the galaxy is evolving in size, and the possible role that might be played by the AGN phase, for example, the Fan et al. Papers. Is there any study or any determination of the sizes of those objects showing this activity regarding those that are not, or any study about that at the different redshifts, of course?
About the sizes of the galaxies and the correlation with AGN activity. Do you mean in terms of the mass? Are you talking about the mass of the galaxy going back?
We know that for let's say for early type objects,
yeah.
If you want passively evolving one,
okay.
For example, okay, if you go above 1, redshift 1, and you see a size evolution that it might change the effective radius by factor 4.
Yeah.
So my point is that whether, and this is like moving softly till today. Okay. So my point is that whether there is any sort of determination of the size and compare it with the, let's say, normal or non-active galaxies.
Yeah, well, there is information about that locally. So objects where the quasar nucleus is hidden, it's difficult to do if you see the quasar directly because that's right in the center, so you can't see whether the central bit's compact. But certainly if you look at radio galaxies nearby, then they look like quiescent radio galaxies of the same brightness in terms of the fact they've got a large effective radius, okay? But that's nearby. And I think what you're saying is that if you look at ellipticals a long way away, they look much more compact. They've got compact cores. I don't think we have information actually on really luminous active galaxies, their morphologies at high redshifts, so that we can compare with the quiescent population. We can do that nearby, but not at high redshifts. So it would be quite interesting to see whether there's any correlation between the effective radius and the type of activity we see.
My point is this is particularly important because the Fan scenario that the AGN it might be the process required to inflate somehow for that reason.
Yeah, so you're talking about the thing about the black holes dispersing the stars in some sense because of binary black holes and all that sort of thing.
Or just the AGN process.
Yeah. Okay.
Okay.
Yeah.
Ejected energy.
Yeah. And just to go back to your caveat, I think you're right that the modelling that you do of the stellar populations is only good as the templates and spectral synthesis models that you're using, and there's a lot of uncertainty. I think for the range around 0.5 gigayears, I don't think you're too much affected by the AGB stars that you're talking about. I think that tends to kick in at above a gigayear, that sort of thing. But there are still uncertainties there, and we always have to bear that in mind, when we're doing this sort of work. I wouldn't say what we've done is super precise. We've done our best, but they're all. What was your other caveat? I can't remember the. Oh yeah, we can take that into account to some degree, because you're right. The Balmer lines, you'll have both absorption and emission from the AGN. But we can actually measure the ratios of the brighter Balmer lines in a lot of these cases quite well. So we can do H alpha, H beta, and in some cases we know the reddening well, so we can actually predict the strengths of the lines and subtract them. So we can do that. And in other cases, the emission lines are much weaker, and it's not a problem. But you're right; that's something we have to take into account. Yeah.
I think Asiana had another question.
Yeah.
Well, thanks for the talk. It has been very good. I have two simple questions.
Good.
One has to do with you have been looking for morphology, distorted morphologies, in order to somehow identify them with possible mergers.
Yeah, that's right.
After you have got to the conclusion of a possible delay between the quasar phase and the starburst phase and so on, at the end you established that there is a percentage of targets in which these two things seem to be more synchronized, so to say, which I don't know if they coincide or not, the proportion with those that you find which are somehow showing signs of being distorted, that you showed at the very beginning.
Yeah.
And then, with going back to this, I just wonder, a question, why are you sure, why can you assure that these features are not due to star formation itself? I mean, if you have strong star formation, not in the case when you have two nuclei, this is clearly a different thing, but when you don't, much of these distorted structures can easily be produced by massive star formation itself.
Well, I think that's right. I think if you look at, say, ULOG's massive mergers, then some of the tidal tails are due to, the original stars in the galaxy being sort of flung out in the disk, the cold structures. But some of the features are stars being formed in the merger. So, but in either case, they're both symptoms that the merger is taking place. Okay. So I don't think I'd be worried if the stars were formed in the merger, because it's just a sign that the merger is taking place, and it probably gives you a higher surface brightness if you've got a strong merger, lots of gas, and that's what we see in our radio galaxies compared with the quiescent population. So I don't think that's a concern for what we've done. I mean, I think the concern is whether these sources are really different from the quiescent, non-active, non-radio galaxy population, and I think we have evidence that they are, but the actual star formation in the merger, I'm not too worried about that, because I think it's a positive sign that the merger is going on. You see it.
All right, and something even more naive. You have questioned yourself what happened with Centaurus 6, and then I question you what happened or what may happen with, for instance, the Antenna Galaxy. So the Antenna Galaxy is something that, do you think it was a quasar before? It would be a quasar in the future?
It could be. I mean, as I say, what we find is that we see the triggering of the quasar over a wide range of radial scales of the nuclei coming together after they come together. And what I think happens is that the quasar can turn on and off during the merger, and it's only on for about 1% of the time. But it just, the gas flows at certain times are enough to trigger the quasar. And I think the trouble is that the merger models don't capture the full physics of that, so they only show it happening at the peak, but it can happen at other times as well. So in the antennae, maybe it was at some stage already, perhaps not a quasar, but some kind of Seyfert-like activity. And then later on, maybe it will be a quasar. I think the thing is that where we see the really highly luminous AGN associated with star formation and mergers, we see them right at the peak. Okay. But you probably have lower levels of activity at other states. The ones that we see later on, where there's a delay, they tend to be less luminous active galaxies. So I think that what could happen is that, in an object like Cen you have the antennae, things merge together, they settle down, you have an elliptical galaxy. And when the black holes coalesce, you get a quasar. So you'll maybe eventually get that in the antennae. But then later on, you see lower level activity, and perhaps before you saw lower level activity.
because a comment regarding that is that in principle, the antenna has all the ingredients that you were asking for,
yeah,
right?
exactly.
The thing you are going to look for with ALMA or whatever.
Yeah.
You already know you have all the CO needed, or you have everything, and also you know that what you are forming in the antenna is a large number of superstellar clusters. The gas is deciding not to go to form the black hole, but to do many more things.
It's an inefficient process, and we don't understand what's going on. Well, yeah, we need ALMA, but yeah.
And that's good. Like this transformation, people can work also.
Okay.
All right, coffee is ready in the library, so I think we can continue the discussion there. Let's thank Clive again.
Okay, thank you.